Okay. Hi, everyone. So I'll get right to it. So we centered the analysis for a study this time around three main topics. I will go through them one at a time. The first is we looked at LES setups and variations around that and methodology on how we consider LES setups is best applied to these types of setups. For that one, we've retained cases 1 and 2. And then for the rest, we focused on case 2, looking at some details of mesh sensitivity, mostly meshing technology. We tried to replicate the workshop grid with another meshing technology that we have in-house on top of ANSA. And then the last one is a little bit for the sake of the exercise, making the analysis RANS to DDES to LES comparison a little bit across the board. Right. Just a brief word on the technologies used here. So when we're not using the workshop grids, we're using Fidelity HexPress grids, which is basically unstructured octree-based hex-dominant meshing. For the RANS and DDES solver, we're using our Fidelity solver, which is a all-MAC finite volume pressure-based solver with coupled for steady-state segregated algorithms for transient simulation. All of our solvers, be it the PBS pressure-based solver or the Charles LES solver, are GPU native, but also have CPU capabilities. When using RANS or DDES, we use SST-based models. When using LES, we use a Vreeman subgrid scales model, and we use algebraic world models and also some variations for the LES that I will mention as we go. I'll start with our LES methodology with a case 1 overview. So in essence, we've looked at different things. The first is the impact of the mesh topology, Cartesian meshing versus hexagonal close back to honeycomb style polyhedral meshing, to a little bit assess the impact on that, on the isotropic nature of the honeycomb meshing. We've looked at meshes that include layers on top of the honeycomb or Cartesian meshes, as opposed to our standard baseline polyhedral approach where you just generate your grid and then essentially cut it in a polyhedral way with the geometry. And we've also looked at the impact of including turbulent inflow into this setup to match the turbulent inflow observed in the experimental setups. All right, so I'll try to, in the interest of time, be quite brief to highlight these impacts. The first thing is, I hope you can see that here. One thing that was shown a little bit also in the presentation of volcano platforms earlier is we're getting these lines, which are transition lines, that we're getting a little bit all around the model when we use our baseline model, meaning we're not inserting layers. And then actually we've noticed that as we insert layers, meaning we ensure a constant y plus over the surface or constant first cell height over the surface, these tend to be significantly reduced, not completely removed, but significantly reduced. And when we include layers and turbulence from the inflow, matching the about 3% above the boundary layer observed in the experiment, actually we almost completely remove those on the average field. You'll still see then a turbulent pattern around the body, but that's all around thanks to the inflow turbulence. And that removes, on average, these spurious lines that we can see. That is basically the solver trying to get to your turbulent boundary layer, but just informed by the fluctuation in the first cell height. All right, next up, as I mentioned, we've compared different packings. Cartesian here on the left, HCP, so honeycomb style packing, hexagonal close packed, packing on the right. And what you can see is that actually, even though the impact on drag is fairly limited here, still when you look at the details of the flow pattern, which is sort of an imprint of the impact of the weight behavior, you can see that using a more isotropic HCP packing leads to better prediction of the weight pattern and a slight improvement in the drag predictions. This being said, results on the left are still quite reasonable, but you can see especially the minimum pressure there is better predicted when using an isotropic polyhedral style meshing. With that, we're moving on to trying to reproduce the same analysis now on case 2, which is maybe a little less clear-cut because of its added complexity. But we've reproduced the exact same analysis, so I'll cut right to it. We've run these simulations for a little under 2 seconds with 1 second for averaging. It's a bit less than what we've submitted to the workshop. For the submission, we've run actually 3 seconds to sort of match the guidelines. But we found that mean calc was reasonably happy with 2 seconds and 1 second for averaging with our signals. Since we wanted to launch quite a few simulations, we've retained that setup to be consistent all across. And we've reproduced that same approach. So what you see, and I will go through also a bit of the details of the local flow pattern. Blue is baseline, so standard HCP mesh, nothing further. Orange is when we add turbulence from the inflow. Red is when on top of that you add layers into the mesh. And then red is the final setup when on top of everything we also include non-equilibrium corrections into the wall function in the adverse pressure gradient regions. And what you can see is the impact on inflow turbulence on the results is fairly limited. The highest impact maybe we can see is on the rear lift, but still not something that brings us completely to the quite the right delta, but it's a step in the right direction. Inclusion of layer further improves on getting closer to the right deltas. And finally, the last blow is really going to these non-equilibrium wall function approach. This will become more evident as we look at the details of the flow. And maybe to start with that, I'm showing both cases 2A and 2B, and then for the rest, I'll show only case 2A because essentially conclusions are quite similar for all of them. One thing we can see is with our baseline setup, we're sort of getting the right behavior here. We've actually run, I'm not showing that here, but some grid sensitivity analysis doing further refinement of the grid. That's actually vanishing as you refine the grid. So it so happens that with this grid level, we're on the right spots. But as you refine, that goes away. And this is illustrated because you can see that when you include some slight variation to the same mesh, so adding layers or adding turbulence from the inflow, suddenly you're not getting quite the right pattern there for the pressure. And actually the way to get that correctly is to keep that same setup with turbulence from the inflow and layers in your mesh, but including adverse pressure gradient effects in your wall modeling. Because then you're right also on what you're doing with your wall shear stress. And I'll go reasonably quicker on those in the interest of time. But we can see that this is fairly consistent overall for the model. We can see rear window, so not only center line, but also off center is also improved when accounting for pressure gradient corrections. We see that the left-right asymmetry in the corner of the rear bumper is somewhat captured at the Z150, but not at the 500 with the baseline setup. But you recover the whole thing when you include both layers and adverse pressure gradient effects into the model. And finally, this imprint of the horseshoe vortex there from the side mirror wave is also better captured when you include layers in your mesh. So when you're removing sort of these artifacts of your inhomogeneous Y plus, if you use sort of a baseline polyhedral CD. Yeah, another impact maybe from turbulent inflow is something that we observe on the underbody center line of velocity. Basically, adding turbulence from the inflow gets us in the right region here for the decay of that velocity downstream RAS, probably because we lack some turbulent mixing in the underbody without this turbulence from the inflow, even though it's quite small, it's 0.25% or 0.26% maybe on this model, it does have a little bit of an impact there, which is maybe also why the biggest impact we saw from this edition was on rear lift. In terms of looking at the individual weights, I mean, I'll go fairly quickly. This would be also in the cross-plotting, but we see that the improvement mostly comes indeed from the layers and pressure corrections as well. Moving on to our mesh sensitivity. How am I doing on time? Yeah, I'll go fairly quickly. Grid sensitivity, basically we've tried to reproduce. There are some minor differences, especially on the rear window topology. We've tried to reproduce the workshop setup reasonably. And what we're seeing is a fairly low sensitivity to the meshing technology when using about the same settings. The only place where we see a little bit of an impact is on rear lift there, which is somewhat consistent. That's where we have the most differences between our meshes, but that also shows that maybe there's a few things that we can improve in some of those meshes. That's where we see the most sensitivity. This, and then the underbody center line as well, and the underbody in general is where we see the most grid sensitivity, maybe showing also that additional refinement may be necessary there to achieve really some grid independence there. Since we've tried to match, but the exact topology is a bit different since the meshing technology is a bit different. Yeah, a bit the same story on all the pressure probes. I'll move on now to my full comparison, RANS to DDES to LES. And essentially what we see is we tend to predict more drag when using scale resolving methods, LES being a little bit better behaved there. All methods seem to be apt at predicting the drag delta on this model. Some of them, most probably because of some error cancellations, because we see that the pressure patterns are much better when using DS and LES, especially LES on this model. Right, and that's highlighted also by the detailed analysis of pressure pattern and drag development. The main area where we see differences are wakes, so front wheel and rear wheel wake, and of course the behavior on the rear window. Right, yeah, this is a recap of what I was saying before. We do observe the same thing in terms of the V3 discrepancy. V5, we seem to observe a better match, but not quite at the level of the total velocity we should get, but the placement of it is quite right with both DS and LES. So we're reasonably happy about that. And that leads me to my conclusions. So essentially, we're seeing reasonable force predictions with RANS, DS, and LES, but RANS most probably due to error cancellations. Scale resolving methods are apt at providing reasonable agreements about all the probes that we observed. And we looked into details of the LES setup where we believe that it's quite important to account for a variety of things. One is ensuring an isotropic seeding of your polyhedral meshes in the wake regions, especially, accounting for adverse pressure gradient effects in the wall functions, and inflow turbulence, which can have a decent effect on your results, as well as the inclusion of layers in your mesh to ensure a homogeneous first Y+ layer on your body. And that's all I have for you today.